All students are in the class. Let me share the screen. Okay, we have just completed one of the tutorial question, which is question 14 in your handouts. Now we look at question 15. So under question 15, there's one graph that tell you the compressibility effect. And this one is on the square object. This graph is on the square object. How do we read this diagram? You have CD, which is your drag coefficient on the left, and then you have Reynolds number below. And for compressibility, we'll link up with the Mach number. We'll link up with Mach number, and we know that Reynolds number is defined in the speed in the upstream velocity. So we can convert the velocity that we get from the Reynolds number here into Mach number. All right. So if you plot, if you can see that if the Mach number is 1, you have a straight line, meaning that you have a constant drag force, constant drag coefficient on this graph, which is equal to maybe 0.75 CD. And then from this CD, you can calculate the drag force that you have on a round object. And if you reduce the speed, the Mach number dropping, you will see the different behavior of the curve also. Okay, right. Now, why do we show you this graph? It says that you can use a graph to determine the drag force that you have on a sphere object. For example, in this case, as long as you have the Reynolds number, you can calculate the Reynolds number, you can calculate the Mach number, then from this chart, you can extend to find the CD value. All right, now the next one is question 16. We will talk about shock wave or pressure wave. We talk about pressure wave. How do we draw a pressure wave? So this is also one of my favorite questions when it comes to final exam. We will test your understanding what happens if you have a certain speed of sound. If your source or you travel in a speed of sound, what happens? Can you draft the pressure wave or not? So on the screen right now, you will see that in the middle, you have a source. It's like in a water tank, you drop a water in the middle, right? In a water tank, you drop a water in the middle, which is C. And then after that, you'll see water ripple. You'll see the wave created by the water drop just now. So it will be the same if you generate sound wave also, right? For example, in the middle here, we have a loudspeaker, right? With a loudspeaker or generate a sound wave or pressure wave at this center. And as this wave moves from the center, meaning that your source doesn't moving, V equal to 0 means the source doesn't moving, and it keep on repeating, generating a sound wave. So what happened to the, how do you draw an object that doesn't move, but create a pressure move in 3 seconds? For example, you draw the first circle, which is the C, radius C. C is the speed of sound. C is the speed of sound. You know the calculation, square root of square root of RTK that you can find. So you can calculate the radius of this one. The radius in 1 second, right? The first second, you get the first radius. Okay, I just explain. Let me write something on the slide here. You know that C equal to square root of RTK, you get in the unit of meter per second just now. Your speed of sound is in meter per second. So let's say this is t equal to 0 and you generate sound wave and you stand here. So after 1 second, you will hear the first sound wave at the distance of c. At the distance of c. First sound wave you see. And then if you stand at this location, you will detect the sound wave from the source 2 seconds or 2c, 2 speed of sound. And if you stand at the distance of 3c, you will receive the sound wave or pressure wave, or you feel the pressure wave after 3 seconds. Any question on this diagram? Before we move on to a more complex diagram. Are you able to understand what is this diagram about? Right. If I ask you to explain this to your junior, are you able to explain what is this diagram about? Are you able to explain? Okay, now this is my favorite question when it comes to exam. So make sure you clear any doubt. If you don't understand, ask me. So this is for 3 seconds. What happened in the exam? I asked you to draw 5 seconds. Draw a pressure wave when the source of the pressure or when your source doesn't move. You draw first circle with the distance of c. Draw second circle for t equal to 2. Third circle, t equal to 3. Draw the fourth one, t equal to 4. Draw the fifth one, t equal to 5. You get 5 marks for this diagram.
Sorry, so each ripple is 1 second?
In this case, yes, because c equal to square root of RTK just now.
Yes.
You get a value in a minute of meter per second. Let's say we get 100 second. 100 meter per second. Let's say, so yes. The radius of this one will be 100 meter after 1 second, correct? After
yes.
1 second, t equal to 1 second. So this is the radius. Then after 2 seconds, 3 seconds, 4 seconds, 5 seconds after that. So in principle, you should know how to draw the pressure wave if the source doesn't move.
Okay, and it also means at t3 is equal to 3 seconds, v is equal to 0.
Means 300 meter from the source. Yeah.
Only at this point, v is 0?
V0 means what you mean?
I mean,
V0.
it's written pressure waves.
Oh, okay. V0, right? V0, yes. What does it mean? It means that the source doesn't move. Meaning
okay, at
that,
all points.
No, only the source means that you hit atomic bomb, for example. You hit at this, and then you doesn't move.
Okay.
Then at how many seconds you will feel the effect? The first round is first second if you stand here. Second one is here. Third one is here. Okay. Now later I will link this one. I will change the velocity later on. Then you will see what happened if I have a moving object with the sound wave. What happened to this shape of the ripple? Okay. At this moment, our object doesn't move, but it's generating a sound wave. So at least you should, by principle, you should know how to draft the shape of the pressure wave if your object doesn't move. This is a very basic shape that you should know how to draw. Okay. And let's say in you found out like at the end you found okay your c speed of sound is 100 meter. So from here I can ask you, okay, let's say if you stand at 150 meter from the source, after how many seconds you will hear the sound wave, for example? The answer is 1.5 seconds. Okay, for example, this kind of application. Okay, right. I'm going to show you.
1.7 seconds.
1.5 seconds. if the sound wave is, if the C is 100 meter per second, 100 meter per second, correct? So if you stand at 150 meter from the source, after you hit a sound wave, or after you generate a sound wave from the source, at how many seconds, if you stand at 1.5 meter, how many seconds after you start press the button, initiate, how many seconds you'll hear the sound wave? The answer is 1.5 seconds. Are you able to relate this diagram with the data I given? Can, huh? Okay. All right, now the second one. Okay, there's a calculation to calculate the radius. We use P wave. So the radius R, which is this one. Just now I give you a very simple illustration, but actually there's a equation to calculate the R. The R is T minus T wave times the speed of sound. Means the equation, the time difference, time difference times the speed of sound is the radius. Okay. Now I'm going to show you straight away. I show you okay, the first diagram first. Okay, just now our object doesn't move, or our source doesn't move. Now our object, let's say you are holding the resonance source, and you move to the left. Okay, the object moves to the left. Okay, with the velocity of v, right, with the velocity of v, but this v is less than the speed of sound. Okay, you are moving your source, right? You're moving your source to the left, but now the speed was less than the speed of sound. So if you want to draw the pressure wave in 3 seconds, what is the shape of that one? Okay, now this is after 3 seconds. So if you have an object moving 1, 2, 3, this is t equal 0. This point, t equal 1, t equal 2. This is t equal 3. So 1 second, 2 second, 3 second. Huh? Okay, this is your initial original position. Okay, how do you draw? If your speed of sound, okay, let me draw the original one. Huh? If it doesn't move, your wave will look like that. If your wave doesn't move, v equals 0, your pressure wave will look like this. But if your velocity to the left is less than the speed of sound, what you mean is that the radius that you travel will be less than the c. Okay, I clear all the drawing. So you will see that the sound wave is not meeting the radius. It's not meeting the radius. So this is at t equal to 3s, means after 3 seconds, in the initial, you start the sound wave. This should be what you hear after 3 seconds, right? 3 seconds. However, if you move to the left less than your speed of sound, meaning you're moving less than the speed of sound, after t equal to 1, meaning from this point, you're going to get the second circle at here, 2C at here. Then this circle at here, for example. Okay. You're going to take some time to understand this diagram. Okay, or you can start by looking at one of the circle. For example, this point, C, second point, 2 circle, and then the third source, the third circle, for example. And you will see the distance between the point is given by the V. Given by the V. So how do you draw this diagram if you have a velocity less than C? All right. The first thing, you start with the source, right? And the distance between source is V. However, this V is less than C. Okay. Now, what happens if you have 4 sources that have the same V? I draw the simple diagram. What happens if your V equal to C and you're moving to left or right? So you know that when your V equal to C, let's say our C in calculation, square root RTK, we get 100 meter per second. So if you move from here, the pulse that you generate, this radius, you know that after 1 second, you'll get 100 meter. And here to here is 100 meter to the second point. Then on the second point also, it will continue to create pulse. Correct? This is a second location, 2. This is 1. But the distance still 100 meter per second. And then the distance from here to here still 100 meter per second if your velocity equal to C at this case, and continue so on. However, if your speed of the source is less than C, for example, if your velocity is, let's say, only 80 meter per second, let's say your speed of sound is 100. So the distance between all these points will be in this form, right? Will be in this form. Okay, will be in this form. Okay, you need to take some time to digest when you have a velocity that less than your speed of sound after 3 seconds. Okay, by giving all these parameter, V, second V, third V, and then we have the radius of each circle. Okay. Now, what is interesting when you have your V equal to C, V equal to C, is that you have a combination of sound wave centered at here. Okay, when you have a source moving, right? When you have a source moving, then and the velocity equal to speed of sound, you have all the pressure wave will intersect at one point here with C, 2C, and 3C. right? So if you start with this location, so after 3 seconds, you're going to hit this one, right? If you start with here, t equal to 0, let's say, you start your signal. So after 3 seconds, you're going to hear it. After 3 seconds, you're going to hear in this circle. And you move the source to here. This source, we're going to generate the second wave here, second pressure wave with 2c. The distance is v equal to c. Right, the distance is v equal to c. So you'll have 2c here. Then after 1 second, you move to this one. You'll create another new wave here. And if you combine the first 3 seconds, you will hear, you create something called tangent plane. We call it Mach wave. You have this Mach wave happen at this location. And this Mach wave is in tangent plane, meaning tangent means if you study circle, there's a one point that is only touching one point, and there's a plane that you can refer to all this pressure wave. And this plane we call it tangent plane. What is interesting is that you have two zones. One zone on the left, let's say you stand here from the source. This zone, you will not hear any sound. We call it zone of silence. On the right, if you stand on the right hand side, you will hear the sound. We call it pressure, or you'll feel the pressure. We call it zone of action, meaning you'll hear or you'll feel the pressure on the right hand side. On the right hand side of the Mach wave, of the tangent wave. Okay, so this is when you have a V equal to C. The next one, if you have velocity, if your source move more than the speed of sound, if your object move more than the speed of sound, it will form. I mean, the tangent plane will change shape into a cone shape. We call it Mach cone. Right? We call it Mach cone, or in 3D, you will have a cone shape region that if you stay within this cone region or Mach cone region, you're going to feel the effect of the pressure wave. And if you stand outside this zone of silence or outside Mach cone, you will not hear or you will not feel anything from the pressure wave. Okay, so these are the phenomena when you travel with a different speed and you resonate with speed of sound. So this is the diagram that you have in your hands-out. So it will take some time to really understand this one. But this basically what we will trying to explain a phenomena. What happens if you have an object travel at the speed of sound and you're standing here? What happened, or how to draw this tangent plane? So it will take some time to draw. So there are two. If you have a speed, you travel at speed of sound, you have zone of silence and you have a zone of action in a tangent plane, in a straight plane, like this one. And this one, if you draw in 3D, it will like a plane, a 2D plane. One on the left, one on the right. Okay, so this one, you need some time to digest this a little bit. Okay, so from V equal to 0, it will look like that. Then when your velocity equal to C, it will look like that. But if the velocity less than C, you will have the right-hand side, left-hand side diagram. If you have a velocity more than speed of sound, you will get this phenomena, and you have a Mach cone. This word will come out when you have a source that travel at supersonic speed or more than your speed of sound. Okay, more than speed of sound. You know that MA equal to V divided by C. So hidden message is that for the first diagram, this is happen when your Mach number equals 0, because Mach number equal to V divided by C. Your V equals 0, you don't have Mach number. This one in the middle, you have Mach number equal 1. You will see this behavior. So when you have a Mach number equal to 1, you will have tangent wave, or you have a tangent plane wave. Then you have two zones. All right, you have two zones, one silent zone, one action zone. And then if your Mach number less than 1 for the left-hand diagram, because your V less than your C, your Mach number will less than 1 in mathematics, because Mach number equal to V divided by C. If your V value less than your C, you have a small number, right, less than 1. For the left-hand side, you have this phenomena. And if you have a Mach number more than 1, you have this phenomena, which is a supersonic scenario. Then you have a Mach cone scenario. And all this will have an angle alpha here. Okay, this angle, we call it half angle. Half angle. Why half angle? Because here to here is a full angle, and we only look at half of the angle from the cone. Okay. So I'm going to move to the next slide. So at your handout, just mark somewhere in your handout that this diagram is very important. Make sure you go and understand this one. Okay. So this one I already explained what is subsonic, sonic, subsonic, and supersonic based on the Mach number. Okay, there's one important equation, which is this one. I want you to write somewhere on the diagram, diagram D, in your handout. So make sure you know. So how to find this angle given by this mathematics formula? When you want to find the angle inside a circle, and you want to find the angle inside a trigonometry equation. So sine alpha, if you want to find the angle of this alpha, is given by sine alpha equal to C divided by V. Meaning is that so you take your C divided by your V. Okay. Or you can take this one is your V. So here, if you draw a triangular, this is your V, this is your C. Trigonometry, you want to find angle theta here. Theta is opposite divided by hypotenuse. So sine alpha equal to opposite divided by hypotenuse. This is 90 degrees. So you take C divided by V, given by this one. And then we know that Mach number equal to V divided by C. If you look at this relationship, is actually is an inverted of your Mach number. Okay, 1 over Mach number equal to C divided by V. Okay, this equation is very important. This equation, it defines only for supersonic V more than C diagram, or supersonic with the Mach cone scenario only. This equation, because all this you don't have angle. Okay, any question want to ask me based on this diagram? Good, huh? Okay, I'm going to move forward. So there's question 16, 1.6. It asks you to fill in, how do we know that it is compressible or non-compressible? Okay, how do we know that our flow is compressible or non-compressible? So this slide is very important when you want to solve chapter 6 question. The first step, you find Reynolds number, and then second step, you find Mach number. If your Mach number less than 0.3, then it's fall under incompressible flow, which is fall under the previous chapter, chapter 1 to chapter 5, if your Mach number less than 0.3. Okay, I repeat, if your Mach number in the question, what you get from the question, if your Mach number is less than 0.3, it fall under incompressible flow chapter, which is chapter 1 until chapter 5. All the formula you can use for incompressible flow. However, if your Mach number is more than 0.3, you need to consider compressible scenario. Okay, the magic number is 0.3. If the number is less than 0.3, then you need to use equation in chapter 1 until chapter 5. Equation in chapter 6 cannot be used when you have Mach number less than 0.3. Chapter 6 only used for Mach number more than 0.3. Yeah, this is a side note for you to decide what equation to use. This is a guideline for you. So when somebody mentioned incompressible, what does it mean? It means the speed inside the system will less than Mach number less than Mach number 0.3. If the person mentioned we have a compressible question, or we have a compressible question, compressible scenario, right? Or in the question you see, assume you have a compressibility effect in the system, meaning your Mach number will be more than 0.3. Okay. And of course, if your Mach number more than 1 means it's a supersonic. If the Mach number less than 1 means it's a subsonic, and so on. This is a side note, transonic and hypersonic. Okay, we look at exercise or tutorial question 17. For info, this question I modified before in one of my final exam question. So also easy question. Okay, right. And this one is lots of application. So you have an aircraft. If you look at tutorial question 17, or you can look at the slides on the screen. So you have an aircraft cruising at 1,000 meter elevation, Z. Above you, fly a pass by. So you go to air show, there's an aircraft move above you. And this aircraft move with a Mach number 1.5. Ambient temperature is 20 degrees C. So after how many seconds the plane pass overhead of you, before, right? How many seconds before you hear the aircraft, right? So based on this diagram. You need to find how many seconds after the aircraft pass overhead of you. How many seconds you hear this aircraft? And again, Mach cone only happen when we have Mach number more than 1 in the diagram that I showed you just now. You only have Mach cone when your object move V more than C just now in the diagram. Okay, now we start solving problem. We know that the Mach number is 1.5. It's a supersonic, and inside supersonic, we will have Mach cone scenario. All right, so 1.5 supersonic. And just now, I already showed you in Mach cone, there's a mathematics calculation. Psi alpha equal to 1 over Mach number. This is from the Mach cone diagram that I showed you just now. And then the definition of Mach number, we already know, equal to V divided by C. All right, so this equation you learned just now, this is before this. You want to apply these two in this scenario. Again, we still back to the foundation question. How do you find the angle here? How do you find? Again, call back the trigonometry equation. Here, you have the Z. You can find the X here by the speed of the aircraft. Okay, the X, you take the velocity times the time, you get the X here. So here and here is a tangent relationship. Tangent alpha equal to Z divided by X here. Anyone of you, you don't understand what I'm talking about, or you cannot see the trigonometry equation? If I show you tangent alpha here equal to Z divided by X, anyone of you don't understand? How come? How come Z divided by X? This is trigonometry question. This is mathematics. Tangent equal to opposite divided by side. Z divided by X. Okay. And then you want to find the alpha. Tangent minus 1 Z divided by VT. Right. Find the VT. Why we need to find the alpha? Why? Because this equation we need alpha. Right? Because it asks you to find how many seconds. Right? So again, back to the fundamental question. How do you find C? You know that your C equal to square root RTK. You go to table B.4. Temperature is given 20 degrees C, so you look at 20 degrees C. Look at the K. Of course, straight away you can read from this table. You don't need to do any calculation. You don't need to do square root RTK calculation. Straight away from table B.4, read the speed of sound. Because we already proved to you that speed of sound inside table B.4 just now. How we get this value? Right? By substituting square root RTK by using the value inside this table. Okay. You substitute all the value, you will get T equal to 2.17 seconds. Anyone want to ask me a question? We have done for this tutorial question. Just for info, this question also one of my favorite when it comes to exam. Okay, nobody asked me question. I'm going to ask question. Chong, are you there? Yes, Praka. Any question?
Uh, for we have to find the mesh number first, then we are got it the angle of
Alpha.
alpha, then how we get the time?
Now you have these two equation, right? Correct.
Okay,
Okay, hold on. I erase all the. So you have equation 1 and equation 2.
okay.
So
Oh, okay.
so how do you find second? How do you find time here? So because uh, uh, you have the alpha,
Okay.
because later you substitute this one, right? You substitute this. Of course, you involve a very long equation. Sine alpha will be equal to sine tangent 1 z divided by vt equal to 1 over Mach number. So you know that the what I call the speed of sound just now from the table. So you can continue this one equal to c divided by v. Again, on the right hand side, you still have the equation.
So we replace the C and V, Z and X.
Uh, no, this one you know. Okay, meaning that okay, what do you have? You have the alpha, right? I mean, you can find okay, you don't have the time, but you have the velocity, correct? How to
Uh,
find the v? Because from Mach number from here. So v equal to Mach number times the c. Mach number is given in the question, 1.5. C you found from table 343.3. 343.3. You have your v, right? So you have v already. So here, uh, so you have your v, or straight away from here also you can solve already lah, actually. So, okay, I continue with my mathematic equation here. So, 3, 4, 343.3 divided by v sine tangent uh, sine tangent 1 z t. So then you will have z equal to 100, 1000. Vt you don't know. Okay, let me do it more proper here. Okay, so we have 1, 2. Then from tangent, you have z, you have v you need to find, t you need to find. Okay, so from here you have Mach number v divided by angle we don't need to find actually. So c from here is 343.3. Mach number is given. So your velocity equal to 1.5 times 343.3. You get your V.
Yeah, okay.
Yeah, your velocity you can find, right?
Yeah, 514.95.
Yeah. So you have one number here. So okay, maybe I highlight this one. So this one you get your V. Then you back to the angle. So angle here you have your V just now, right? The
Yeah.
V. And then what else? What else we have? Mach number you have. So sine, there's a conversion, trigonometry conversion. Sine tangent minus 1 sec Vt equal to 1 over Mach number 1.5. So you will have sine tan minus 1, z is 1000 divided by V, you have one number, and times the t equal to one number. So here is only a trigonometry conversion. At the end, you can find the t. Okay. So, or you can transfer the sine to another side. You understand now? Sine tan something equal to 1 over 1.5. This is a constant value, right?
Yeah.
So what you can do, you can sine minus 1, this value. Means you pull your sine to another side. Then here is a constant value already. So tan something, this also one value already. Right, something t. Move your tangent to another side. So inverted t to another side. So you have 1 equal to tangent constant value. Then here you can find your t. Okay. It's more on mathematics steps, so I don't want to go into. But what is important here is you understand we are using these two equations.
Okay.
Because in exam I will change the scenario also. Okay. Important is that you understand that when you have in what scenario you have a Mach cone, is that when you have a supersonic. All right, try to understand this table, this diagram. All right, how you get sine alpha, this one. So this question actually testing the application of these two equations. Then
Sir?
apply. Yes.
I understood everything, but just the last one. I mean, where did you find the teeth?
Yeah. Okay. I'll repeat one more time. So this is going to take a while. Okay, you have these two. Then you have tangent. Oh. Okay. So you have, okay, you have alpha equal to tan something. So sine tangent minus 1 z v t equal 1 over Mach number. So sine tan Mach number is given. V you need to find. V you can find. Okay. Z Vt equal to 1 over 1.5. 1 over 1 of 1.5 equal to how many? 1 over 1.5.
0.67.
Yeah. 0.66667. Okay. So sine 10 minus 1, 1000 VT. So you move your, okay, I continue here. So when you move your sine 10 minus 1 something, 0.667, move sine from left to right. Sine minus 1, 0.667. What's the value?
Uh, 41.84.
Okay, 48, 48,
41.8.
40.81. Okay, so tangent minus 1, you have 1000 divided by Vt. Okay, again, put your 10 to another side. Tangent 41.81. You have 0.89.
0.89.
Okay, so here you only have V and T.
1000 over 0.89.
Yeah, so okay lah, 1000 divided by 0.89 equal to Vt. 1000 divided by 0.89. So you have 1123 point something, 0.59 equal to Vt. So what is the value of V? Here. So how to find V? V equal to
Max number
M.
is 1.5 and C
Yeah.
from the table.
Yeah, so how many? 1.5 times 3 something?
3, 4, 1.
3, 4, 3, 4, in table, let me see. Okay, in table, 343.3. 343.3. Okay, let me calculate. 1.5 times 343.3. 514.995. So 1123.59 divided by 514.95. Get it up.
2.18.
2.18.
Yeah lah.
Same.
112.59 divided by 14. 2.18 lah. Answer is 2.18 lah, about lah. Because just now we do some rounding on the decimal place. Okay, do I explain clearly to you?
Yes, sir.
Okay, right. So again, the learn about the principle, the strategy we solve. We use sine alpha equal to 1 over Mach number, with this one, and we use the Mach number definition, ma equal to v divided by c. How to find c? You can use square root of RTK, or you can straight away go to table B.4 for standard atmospheric at 20 degrees C. Then go to find the C, substitute inside. The rest is just I will call is mathematic solution. Means just now you see a lot of step here. All right. So I think most of you confused with the sine and tan. How do you proceed from there? I think that is the most of the problem lah. Not because of the formula, because of the transfer of sine and tan, and also cos sometimes, cosine and all this. Okay, yeah. So improve on all this, the trigonometry, what you call trigonometry equation. Okay, I think we spent a lot of time in this. Okay, we move forward. Okay, we now go to question 1.8. All this you fill in later. So what does it mean if we have isentropic flow? What does it mean? Isentropic flow. We will have the following assumption. Flow steady, no extra body force, no friction, no heat transfer. This one already tell you this is adiabatic. Do not pass through a shock wave. This one is a compressible effect that we see just now in the diagram. The tangent cone and all these tangent plane or the Mach plane or Mach wave and the Mach cone, this one, if we do not pass through, then we don't have loss of energy. Okay, these are just a fundamental reminder that what happened in our steady isentropic flow. So when the question say that it's adiabatic and reversible, means that we have all these settings. Means we don't need to consider friction, heat transfer. There's no heat transfer. There's no problem on the passing through the shock wave. And entropy, the S, all these are constant. Now we look at one example. So this one also, I will say that this question on question 19 in your hands up, you need to refer to figure DI. Figure DI, which is just now we see table DI. This figure that you see on the screen, this is the transformation of the table, meaning this one is in the graphical illustration. Okay, so if you look at your hands out, if you look at table at page number 6 that I explained just now, it actually is the same with the graph that you see on the screen now. On the screen now is a graph form. The one in your hands up, page number 6 in tutorial, table DI, that one is more, you can use that table to identify the parameter, or you can straight away use this graph to use. Of course, in exam, you know our style, that we always want to see whether you know how to use the table and graph. Okay. So let's try to understand this question and how do we use the table or we use the graph. So because this question you can use both method. One is from the table D1 table, one is from the graph. All right, now we have this scenario where we have a change of our profile. Before this, we all look at very straightforward pipe, straight pipe, and this one now we look at different geometry of the pipe. Okay, now this pipe we have 2 points, and the temperature, pressure is given. Pressure is 0.34 megapascal, which is here. And temperature T1 is 38 degrees C. Velocity at this point is 150 meter per second. At a downstream, this word downstream means point number 2 or point after point 1. Downstream means a point after the reference point. Downstream. This is upstream, downstream. Okay, upstream, downstream. Upstream is on the left. Downstream is on the right, depending on the arrow of your flow. Depending on the arrow of your flow. At the downstream, the Mach number is 1.8, means when it comes to point number 2, the Mach number become 1.8. The flow is steady and isentropic. The keyword given here, isentropic. Okay. Now, if you see the word isentropic, straight away go to table D.1 or graph D.1, because under the graph or above the table D1, you will see the word isentropic flow. I give you hints already. If in the question you see an isentropic, straight away go to table D.1 or D1 or DI or graph DI that will show you the hints isentropic flow of ideal case 1.4. Straight away use this graph or use the table 1.D1 just now. Okay, this table, maybe most of you, this one. Okay, the one that we find stagnation pressure, temperature, that one. Okay. Okay, let's continue to solve this question. Huh? Okay, now what is the strategy? What is the strategy is that from the Mach number, again, we extend slowly because we have Mach number. So we can find velocity from the equation of Mach number. Okay, you arrange, you get this one. V equal to m times c at point number 2, because you have Mach number value, you can find V2. So you know that C2 equal to square root of rho KRT, right? You need to find this one, you do not know the temperature. K, maybe you need to check. R, you need to check. Huh? So of course, most of the time K is 1.4 because we are using the isentropic case. Isentropic case, most of the time you use 1.4. R, you need to refer to table 1.8 based on the medium that we use. In this case is air. Okay. All right. Then the energy equation, this one, bear with me for a while. We're going to look at this equation later on. So from the equation, we will have Cp times T plus V component. Okay. At this moment, just accept as it is. You will see one slide later on about this one. Okay, this example we need to use equation for adiabatic flow. So this is just a special case. All right, we will see this equation later on. So at this moment, just accept this equation. Later you will see one slide specific to explain this one. How this one come into place. Huh? Okay, and again, this equation apply for adiabatic flow only. Adiabatic flow. So yeah, so these are all the keywords. You substitute the equation for V2, this one, the whole thing in here. The rest is just a rearrangement of that. All right, so look at the screen. Stop me if you not understand, because all this you can find in my slides later on. Okay, the rest is just mathematics rearrangement. Important is that the first one, call out the Mach number definition, find the V2, use the energy equation that you see on the screen now, substitute the Mach number equation inside here, rearrange, fill in all the particular that you have, because inside here you can find the Cp value. Cp you know how to find already by using the R and K value and T value, right? Definition of Cp you can find, and T is given, T1 is given. Again, T need to change to Kelvin. V1 is given, so you can find what is your T2, okay, in Kelvin. All right, and then from there you can find your V2. From the T2, you substitute back to the definition V2. Okay, after you get your T1 and V2 from these two equations, from the Mach number equation and the energy equation, you find T2 and V2 here. And then the question asks you to find the pressure, right? Because we have the temperature already, velocity already, we need to find the pressure. We need to find the pressure. So since it's an isentropic process, again, call back the isentropic equation that I asked you to copy just now, the pressure ratio and the temperature ratio equation. Okay, if you forget, I will flip back the slides. It is this one. This one, this slide. This equation, I ask you to copy. That's why I say that this equation is very, very important. This one, always call back when you have an isentropic flow. Apply to this one, and this slide is for all the isentropic. Your S is constant and all these. So apply equation because you want to find the pressure. You move this equation into place. We move this equation into our calculation. Let me find the slide. Okay. Okay, so this equation you find in the isentropic slides. Isentropic P ratio, density pressure, density ratio, and temperature ratio that I showed you just now. The three brother, very very good friend. You remember their relationship with the K. Right? Since we have the T and T2 and T1, substitute, you have the K value, you have the P1 value, you can find the P2. What else? And then this is just inverted to find back the Mach number at 0.1. Just a revert. This is just a checking because the question, I think it do not ask you to find the Mach number at 0.1. This is just a check back because in exam we might do the same way where we ask what is the property at another site with the parameter you have. So this is just to use back the V velocity at 0.1 and then calculate the speed of sound at 0.1 using the parameter given. So you will find the Mach number at 0.1 is subsonic 0.43. Mach 2, point number 2 is 1.8. So from this diagram, you will find that when you have a change of geometry of your tunnel, subsonic, when it come out, it will become supersonic. And then other thing is just to find the stagnation pressure. What is the stagnation pressure and all this? I show you already. This one, the interpretation process just now. So when you have the Mach number, refer to the table D1. Do the interpolation for Mach number 0.43. You get a ratio inside the table. And you have a P1. So rearrange this equation, you'll find the stagnation pressure. And so on. And this is point number 2 also. Point number 2, 1.8, go to the table D1. Use the interpolation. You'll get the ratio of the stagnation in the table D1. You'll get this one. So what I'm talking about, all this number is from table D1 that come together with question 14 just now. This one, question 14 about the airline. We are referring to this one, table D1, this one. It was given together with the question 14, 1-4. The complete table is not this small. It's a very big chart. I want you to go familiar with the table D1. So you need to do a lot of interpretation by giving with the Mach number. Okay. Okay, then the rest you can read my slides already. The rest is just mathematics equation to find the parameter needed. Once you have all the ratio from table D1, you substitute to find P2 divided by P1. This is just a mathematics strategy we solve. So P2 divided by P1, you take, okay, let me mark. Let me draw a line. This is 0.1, referring to here. These two, referring to 0.2. So to find the ratio between 0.2 and 0.1, P2 divided by P1, what you take is that you take the ratio at mark 2 here, 1, you take point number 2 divided by point number 1, which is you take 0.174 divided by 0.88. Okay, now this scale is important for your final. The number will change, but you have to know how to find all this ratio from table D1 interpolation, and then by using the interpolation, you find the required pressure. Okay, so from here you can find the pressure at point number 2. Okay, so this is the same the previous one. So T2 also same, apply the same. V2 also same. So okay, so there are two methods here. One is using velocity. Sorry, one is using Mach number definition and energy equation to find. Another portion is using table D1 or DI or graph DI. Graph 1 is I will show you in another tutorial question. Right, this example I will use table DI to show you. So table DI to find the from the stagnation pressure, we find the P1, we find the pressure and temperature at 0.2, and velocity also. Okay, this slide you will have it. I think most of you already have it if you already download from the Moodle. So go through this example. All right, it will take some time to digest. So I know that there's lots of equation, but the start is very simple. Okay. Any question about this tutorial question? Okay, maybe I rephrase. So what does this question trying to test you? Okay, what are the keywords that every time you see this you have to stand by? So you are given a geometry, and this geometry was changing. It was not a straight pipe anymore. So for chapter 6, you will see there's a diverging and converging section. This is called converging. This is called diverging. So it means that you have a narrow change of area here. Then you will have P1 value, T1 value, or V1 value, and P2 value is unknown. T2 value is unknown. V2 value is unknown. All right. Mach number is given here. So how to find P2, T2, V2? This is the question trying to ask you. You need to find P2, T2, V2. Okay, what are the strategy? You can use table D1 or graph D1. Graph D1 is this one. So I will show you how to use this one in another example, not this example. Okay. So what are the strategy we use to find P2, T2, V2? Definition of Mach number, equation, energy equation. These are the first strategy we use. From these two, you find your T2, V2. Okay, from this definition, Mach number definition and energy equation, you find T2, V2. After that, you use isentropic equation, which is the ratio pressure and the temperature ratio with the K, this one, to find P2. So you have V2, T2, and P2. Another method is that you use table D1 to find the value. Because in table D1, you only have pressure ratio, you have the pressure ratio, you have the temperature ratio in stagnation, and you have density ratio also. And however, in table D1, you always refer to Mach number. All these are leading by Mach number. So by finding what is the Mach number at point 1, and using table plus the help of table D1, you're able to find, okay, you're able to find what is your P2 here. And also you can find T2 also. Then from there you can find your V2 by using the Mach number and the speed of sound, square root of KRT. So there are two ways to solve this question. Okay, I will highly recommend the second question where you use table DI, which is from this step, from this slide. Okay, any question? No question, I'm going to ask question. Okay, I'm going to ask, let me close screen first. I open up one file. I'm going to ask question. Okay, I'm going to share my screen. Okay, I'm going to ask someone to use table D1. Okay. Now, explain how do you use table D1 with Mach number 0.43. Okay, Mach number 0.43. How do you find 0.88 value? Okay, I repeat. I'm going to ask someone to answer this question. Let's say your Mach number is 0.43. Tell me how you use table D1 to find stagnation pressure value at Mach number 0.43. Okay, I'm going to show you table DI, you're going to find stagnation pressure at Mach number, what is that already? Mach number 0.43. Tell me what is P divided by P0 value. How to find, So this is a very quick question. I'm showing you table D1. I want you to tell me what is the pressure ratio at Mach number 0.43. Okay, let me pick one of you. Praka, are you there?
Yes, sir.
Okay, now looking at the screen.
Okay.
Okay, you can give me instruction. How do you find value of stagnation pressure ratio on table DI? If your Mach number is 0.43, what is your first step?
We have to find the 0.45 Mach number
Okay,
above
okay, okay, okay,
Mach
okay.
number and
Where
below.
where is it?
At the first line, ME.
On the left or right? You have two sections.
Left.
Okay,
On
left.
left.
Then
Because they are giving a 0.434. On the
okay,
left, the
so
0 point, they're starting
here,
from 0.4.
okay.
Yeah.
So I'm
We are taking the two numbers. It means 0.43 above and below.
okay, so
It means
we're going to look at
0.4
here.
and 0.5. Yeah.
Okay, I'm going to extend this one, extra this one. Okay.
Okay. Then we are
0.43. So we here.
Yeah.
So okay, maybe I smaller a bit. So you want to find what pressure ratio?
Pressure for we are taking a 0.8956
So this
and
one
0. Yeah.
and something
Then we
here.
are doing then we are doing a interpolation formula.
Okay, good.
Yeah.
Right. So at least you Praka, you understand. Okay, now I'm going to ask somebody else. Let's say now. Okay, Praka already explained how to get that one already. I'm going to find. Okay, let me erase. I'm going to ask someone else to find. Okay, this one I already asked you already. So let's say now your Mach number is 0.5. Give me the value of temperature ratio of T over T0 at Mach number 0.5. This is the second question. This one solved already. Okay, now based on this diagram, based on table D1 for isentropic flow function K 1.4, now in your calculation, you found out that the Mach number is 0.5. What is the value of T over T0 from this table? Are you able to find, or are you able to tell me the value? Okay, I'm going to ask someone. Okay, let me find. Who else I haven't asked today? Joshua. Joshua, are you there?
Yes, sir.
Okay, now I'm going to share my screen. Okay, you are using PC or handphone?
PC, sir.
Okay, PC, so I think you can see very clearly. Okay, now I'm showing you the table DI or D1. Now you have a Mach number 0.5. What is the value of T over T0 in this table? How do you find? The first one, how do you find? Where do you go first? You look at left-hand side or right-hand side, because this table you have two portions. One is 0 until 2. Right-hand side is until 2 until 10. Which portion you look at first? Left-hand side or right-hand side?
Left-hand side, sir.
Left-hand side, okay. Then go to
0.5.
0.5 here.
5000. Yeah.
Okay, so what is the temperature ratio? What's the temperature ratio? What is the temperature ratio of T divided by T0 or stagnation pressure from this table? What is the value?
Okay.
What's the value? Maybe smaller. Huh?
So the table is shaking.
Yeah, okay, now you can see, right?
Yeah.
Okay, what's
Yeah.
the value?
For T naught is 0.9524.
Okay, good. So now I extend the question now. So you get the value of 0.9524, right? Now
Yeah.
what happens if your temperature at point 1 is 100 Kelvin? What is the temperature stagnation pressure? What is the stagnation temperature? Sorry. If your answer is 0.9524, right? So let your temperature at point 1, let's say you have 100 Kelvin. What stagnation pressure at what is the stagnation pressure at this point? At point 1. What is the value? You already have the ratio 0.9524. What is the value? What is the temperature ratio? What is the temperature Kelvin? What is the temperature?
Sir, 104.
Again, what's your value?
104.9.
104.9. So your answer is 104.99 something
Yes,
lah, Kelvin. Okay, so
410.
okay, good. At least you understand. Okay, now I won't ask anymore. Any one of you still don't understand how to use table D1? We have 2 examples just now already. All right, anyone still don't understand? Still need me to show you how to use this table to find isentropic flow? Anyone? Let me know. Huh? At least we learn together. At least we know that, okay, you still not catching up. You need some time. And we're going to help you. Okay, we're not going to let anyone behind. Huh? If you don't understand, never mind, just admit that you don't understand. Then we will teach you. Okay, good. Huh? No, nobody asked me question. Then I assume all of you know how to do in final. Okay, good. The rest you read my slides. The rest is just interpolation or ratio between these 2 cases. Okay. I want you to go home and read from my slides. This is about Bernoulli equation. In Bernoulli equation, we assume incompressible flow in principle. So in idea, every time you mention Bernoulli equation, when you use this form, P plus half rho V square plus specific weight times the elevation equal to a constant. When you use this equation, we assume that the flow is incompressible. And for isentropic, isentropic equation, we always assume we have an adiabatic, means that we don't have heat transfer in and out from the system. Okay, so we will use this equation. Pressure at any location, from the Bernoulli equation, we can use P equal to P0, stagnation pressure, minus half rho V square. This is a new equation that you need to learn for today. And every time, if the question asks you to find stagnation pressure, don't tell me you don't know. I already asked 2 persons to demonstrate how to use table DI already. So you should know. So every time you see a stagnation 0 and isentropic, straight away go to the table and do interpolation. Okay, you should not have any question on that. The rest is just this one is just a derivation of the equation. You go home and read and how it comes to this form. It's a very lengthy derivation. at the end, it's just proof that you can use this equation. Okay, you can prove that just now. You just prove that this statement. Okay, P equal to P0 minus half rho V. So if you want to find stagnation pressure, you can pull your second term, this one, negative to left hand side, become positive. You can find the P0, or you can straight away from the table DI just now. Okay. This one is, again, I have to remind this one. This equation, or the equation I showed you just now, P0, which is very near to P plus half rho V square. This is only for small Mach number isentropic flow, very small Mach number, which is less than 1. Okay, this is an approximate Bernoulli equation in an approximate scenario. Okay. Another one is called critical state. This word also popular when it comes to final exam. What mean by critical state? Every time you see the word critical, we will use star. Okay, in the equation, we will use star. So this equation you've seen before. When we have a critical state, our Mach number, remember, always equal to 1. When you have P star, pressure at P star will happen at Mach number 1. T star or T critical happen at Mach number 1. Density star happen at 1. Area star happen at Mach number 1. Every time you see a star, it means the Mach number at that particular point always equal to 1. Okay, this is the summary of what is critical state. The rest you can read from my slides. Yeah, every time the question asks you to find critical state at a certain point, meaning you go and find the star, or the Mach number straight away equal to 1 in all the equation. Okay, I'm going to show you what is important. Equation that is important is this. Okay, is highlight this equation to find stagnation pressure, stagnation temperature, and the critical temperature with this equation. And the rest you just related to the temperature ratio just now. 2, 1, 1 with the K, with something K just now. K divided by K, that one. Okay, you just modify this one to a star, and then the bottom becomes 0. The rest is the same. Okay, and if you look at the diagram, this one is under question 24 in your hands up. Question 24, there's a diagram there. So today you learn about new graph. We call it T versus S, temperature versus entropy. T versus S graph, T versus S entropy graph. So in an exam, this also we want you to know how to plot this graph. So how do we start to plot this graph? The first two lines that we're looking at is this one. First line, T0, which is you derive, or maybe it will be given. This one is a temperature star, which is a critical star. And again, every time you see a star means all the point at this, all the Mach number at this point will be equal to 1. And if you relate this point and this point, star point and 0 point at stagnation pressure, temperature, what happened to the S? What happened to the entropy from this graph? Okay, let me ask question. Let me ask someone. Bilal, are you there, Bilal?
Yes, sir.
Okay, I'm showing you the screen now. Okay, so this is the graph T versus S. All right, I'm going to guide the question. So let's see if you're able to answer. What happened? The question. Here's my pen. Okay, my question is that what happened to the entropy at the point of T star and T0 at this graph? What happened to the entropy between these 2 points? What does this graph tell you?
That this is the critical state, correct?
Yeah. What is the value for these 2 points? What's the value of entropy for these 2 points? What happened to the entropy value at these 2 points? Does it different or does it same? Let's say I put 0.1, 0.2. What is the S value for 0.1 and 0.2? What's the S value? Does that different or does it same? Do you understand what I'm asking?
Not exactly, sir.
Okay, now my question is that, let's say you're able to see the screen, right? You're able to see the screen? Okay. Now,
Max
you
is
have,
1, the max number for this case.
yeah, I'm asking you, I'm giving you 2 points here, 0.1,
Okay.
0.2. So, and then I draw a straight line. These 2 points, I do a straight line. My question is that, is there any difference on their entropy value?
Entropy should be the same if it's a straight line.
Yes. So yeah, I mean the answer is same. So for 0.1, 0.2, the entropy is the same.
Okay, I'll
Right?
try to use the number.
Yeah. So
Okay.
yeah. So this is the way we draw this graph. First, you draw the stagnation pressure, stagnation temperature. Then you draw the critical temperature. Step 1, step 2, draw the solid line. Then from the critical state or from the isentropic process definition. Okay, isentropic process definition, your S is constant. Straight away, draw a line of your S, meaning you connect these 2 points together. And then you followed by pressure line. Pressure line will always, if you draw T versus, if you learn about thermodynamics before this, you know that if you draw T versus S, the pressure will always go like that. P1, P2, maybe this one, P3. Always have a diagonal angle. So you just bypass the intersection point. You draw this line as a pressure point, draw this one as a pressure point, and again this one pass through a critical point, which is a star. So this one becomes star, and you get the value, or not value, you can draw the line on the TS diagram. Okay, all these are just explanation on the equation that we involve here. Okay. The equation here is on the slide. Right, it's on the slide. Now, important equation is this one. You convert this equation into pressure, convert this one into temperature, again with the K ratio, K ratio exponential. Okay, standard. And then the next one, I want you to read from the slides. I'm not going to read all the thing. I want you to go home and read about it. Again, this is just to remind you. I show you this graph, this slides when we do about continuity equation. I think this one is in chapter 3 before this. So when you have incompressible, your density always constant. However, when it comes to chapter 6, your density change, cross-section change, which is your A, flow velocity V. All this will link up with the pressure. That's why in table D1 just now, you will see pressure, you will see density, you will see area. Okay, and all this happen. And then I want you to read this slide. I'm going to skip this step, but it's important for you to read. All these are just an important point I extract from textbook. I will not go and go into detail. But what is important is this equation. Okay, the rest is just a derivation of this equation. So I'm not going to go through the derivation step. You go and read through my slides. They are very clearly stated in my slides. Okay, read through. You see at derivation. Now these slides give you three equation. This one, and this one. So this one, these three equation is linked up with area. These three equation link up with what happened to the area. Okay, what happened to the area? And then these two notes also remember. Now, if you look at just mathematics equation on the screen, if your Mach number less than 1, which is subsonic, so let's say we look at this one. We look at this equation. So what happens if your Mach number less than 1? Let's say you have your Mach number 0.5, let's say. So 1 minus 0.5 square. You will get volume. You will get the area will become positive. Okay, if you do the mathematics calculation, if your Mach number less than 1, the equation inside will become positive. It means, or same with this equation also. All right, it means that your density and area will change in the same direction of your flow. But however, if your Mach number more than 1, density and your area will change in the negative direction. Okay, this one you take some time to go through. I'll give you one diagram that it will be helpful for your coming exam, which is this one. This diagram is about converging and diverging duct. This is question 13, or it is in your page 14 and 15, which is will help you through. So if you see this one, okay, I show you the technical word first. The first one is diverging. Diagram A. Okay, no, diverge, no. Okay. Diagram A, this one, this one. This is called diverging, means small area can become bigger area. 1, 2, area 1 smaller than area 2. Means the area, area 1 is smaller than area 2, meaning the area is increasing in the diverging duct. This is converging, meaning area is become smaller and smaller. It's important, because sometimes the question will ask you to explain the phenomena. Or sometimes the question do not give you any diagram. It will just mention in a diverging duct. So in a free body diagram, we expect you to draw something like that. So you draw a diverging duct and then you do the calculation. Converging duct is this one. You draw something with the big area cross section, and then you draw a cone and come up with a small area. So diverging, converging, and this is the note, a short note for what we expect to behave. I mean the flow will behave. What happened? So if you have a diverging, if you have this configuration in your system, and your flow is subsonic, means from here, it start from a very small, low number, flow number, Mach number, subsonic flow. You see your dA will be positive. The equation on the left, your dA will be positive. Your dV will be negative. Supersonic also. Right. So this one you can refer back anytime. So what is important is the word diverging, converging. And you can combine these two small components into a complete wind tunnel configuration. So diagram A is called converging diverging duct because it's converged first, followed by diverging. Diagram B, you break into half. So small to big is this one, is diverging to converging duct, become like that. Okay, so these are the new technical words that we expect you to know when you study about fluid mechanics. So when you talk about converging diverging duct, or in a converging diverging duct, analyze pressure at certain point. So before you solve question, in your mind you should already have what is the setup of the duct. If you're given converging diverging, then you draw this diagram. If you're given a diverging converging duct, then you draw this diagram. Yeah, all these are free marks. You draw this one, you get marks on. So based on the question. And then, yeah, all these are explained already. And this table is going to help you when you try to solve question. What happened to the Mach number when it's subsonic? What happened to a velocity, temperature, pressure, decrease, and all this? Okay, we have converging, diverging setup based on this equation. Okay, is on when we want to focus on what happened to the cross-section area A. What happened to the cross-section area when we have a certain setting in our flow. So this table will help you. What happens if you have an input less than 1, m less than 1? What happened to the velocity? Which means I take the first example. So if you have a converging, how do you use this table? If you have a converging duct, converging means big area to small area. Right, the flow, big area to small area. So what happened in this setup is that if you have a duct, I draw a cone. What happened to the flow from point 1 to point 2? Right, point 1 is here, point 2 is here. What happened to the v velocity? In this table, if you have inlet Mach number less than 1, meaning your speed is very slow, from big area to small area, velocity going to increase at point 2. Meaning, if let's say your velocity at v1 is 50 meter per second, if you have a converging passage, when you reach point 2, it will be more than 50 meter per second. So this one you need to find. It's just a double check of your answer. If you get 40 for this setup, then your answer is wrong. Okay, if you get 60, then probably is correct, for example. Okay, this table is going to help you to check your answer, whether your answer is correct or not. So I'm going to explain about this one. So if second scenario, if your Mach number more than 1, meaning very high speed, for example, 400 meter per second is more than 1 Mach number. So what happens if your flow is very high speed, 400 meter per second in the converging passage? When it come up point 2, the velocity will be less than 400, for example, 300 meter per second. Then the answer might be correct. If your answer, you calculate your V2 is 500 meter per second, then your answer is wrong, because it is not possible that your speed will become larger than the input when your Mach number more than 1 in the converging passage. This is how we use this table. Any question? Okay, just to test your, yeah. Okay, just to test your understanding before we end today's lecture. By looking at this table, I'm going to ask each one of you. Okay, by looking at this table, I'm going to erase all of this just to test. Okay, the first one I'm going to ask. So, let's say you have a diverging, you have a diverging setup. By looking at this table, I just want you to tell me whether it is possible or not. The answer is possible or not, or why, based on this table. So let's say your flow from here, and you have a diverging passage. Okay. Now let's say your velocity measure at point 1 is 100. My question is, when it comes to point 2, this is point 2, this is point 1. When it comes to V2, it is possible that let's say your V1 is 100 meter per second, and you know your Mach number your Mach number, let's say your Mach number 1 at the speed, Mach number speed is 343 meter per second. It is your C value is 343. C value 343 meter per second. And now your velocity at point 1 is 100 meter per second. Okay, you need to know how to use this table. So is this possible? My question is this possible your V2 to become 200? And why? Is this possible? Okay, I repeat the question. The scenario is given below. If you have a diverging passage, and given that if you, from your calculation, your Mach number, you know that Mach number equal to square root rho RTK, and you know that your Mach number, your speed of sound is 343 meter per second. Okay. Now, you from the experiment, you measure velocity at point 1 is 100 meter per second. Is this possible or not? My question now, is it possible or not in this setting, V2 get 200 meter per second? It is possible or not? Okay, I'm going to ask question one by one. Then we end today's lesson. Okay, I ask Praka first lah. Okay, Praka.
Yes, sir.
Is this possible to get 200 meter per second based on this table? And why?
It is not possible because
Why?
the mesh number we are calculating with a mesh number.
Okay.
It is less than 1, so
Okay.
it is subsonic. So
Subsonic.
if a subsonic, the velocity is decrease. It won't increase.
Correct. Right? Because from here, diverging passage, and our input is subsonic because we know that our Mach number is 343. Not Mach number, our speed of sound is 343. Our speed here is less than 1, so we get Mach number less than 1. So based on table, your velocity should be decreasing. So your V2 should not more than 200. Okay, now the next question. Still same setting. Now I increase my, okay, I give you the temperature. Temperature 1, for example. Temperature 1, you measure at 100 Kelvin. Is this possible? You get 200 Kelvin at point 2, and why? Is it possible? Okay, my question still the same. The same setting, you have the diverging passage. Mach number still 343. The velocity is 100 meter per second. Now you measure, you have one more parameter add in, which is the temperature at point 1 is 100 Kelvin. Is this possible? When the flow come up from point 2, it is possible to reach 200 Kelvin, and why? Based on this table, it is possible to reach 200 Kelvin. Okay, I'm going to ask the second one from team. Bilal, are you there, Bilal?
Yes, sir.
Okay, is this possible to reach 200 Kelvin?
It should be possible because temperature increases in the
Yes.
diverging passage.
Correct. The answer is correct. Okay, good. Now I'm going to continue with the pressure.
Sir,
Now,
can I ask
same. Yeah, okay, good. Bilal, you already, not Bilal. Is it Bilal? Yeah, Bilal, you already answered the question already. Thank you. The next question I'm going to ask Chia Weng Fong. I changed this question to, now, what happened if, okay, I change a little bit. What happened if I flip the diagram? The next one I'm going to ask Chia. Now I change the dark setting. Now I have a converging passage. Point 1, point 2. Okay, I'm going to erase some of the notes here. Okay, Chia, my question is, now I have a converging passage. Mach number still same. Speed of sound at point 1 is 343 meter per second. Velocity now is 100 meter per second. Is this possible to get velocity V2 at 200 meter per second, and why? Is this possible?
Yes, possible.
Why?
Because the Mach number is still less than 1.
Okay.
we follow the less than 1, the velocity can increase.
Increase, so is this one, okay, good. Okay, the next question will go to Vina. Next question, Vina. The next question go to Vina. Now also the temperature. The same setting, the speed of sound at 0.1 at the entrance of the converging passage is 343. Velocity still at 100 meter per second. The temperature now is 100 K. You measure. Is it possible when the flow come up from 0.2, it will reach 200 K? Is it possible and why? Vina, are you there? Vina, are you there? Okay, I will ask Vina again. Sue, are you there?
Yes.
Okay, so based on the same question, when you have a converging passage, right? You have a converging passage, your speed of sound at 0.1 is 343. The velocity at 0.1 is 100. Temperature at 0.1 is 100 K. So is this possible when the flow come up from 0.2 will reach 200 K and why?
We will not reach the 200K.
Okay,
because
why?
from the table we can see that the mesh number is below than 1, then it will decrease.
Okay, good, correct. The answer is correct. Okay, now I'm going to change to okay, right. The next question. Okay, I let the next question will go to Brian. Brian. This question go to Brian. So Brian, now the case changed already. The velocity no longer 100. The velocity now become 400 meter per second at 0.1. Speed of sound still same at 0.1, 343. Is this possible when the flow reach 0.2? Is it possible if your calculation is 200? And why?
Is that for
Yeah, in this setting, yeah. Converging passage. So now your velocity is 400. Is this possible in your calculation when it reach 0.2? Is it possible you get some answer around 200? Is it possible? And why? From this table.
Not impossible, sir.
Your answer is what?
Impossible.
Why?
Since it increases, since Mach number is
what? Mach number is what? Is what? Is more than 1 or less than 1?
less than 1.
Huh? Less than 1? Mach number less than 1. Your speed of sound is 343 and your velocity now is 400.
Oh.
How you find your Mach number?
Just a moment.
What is the equation of Mach number?
V over velocity over speed of sound.
Correct.
It said the velocity is 400, right?
Yeah, 400. C is 343. So is left hand side or right hand side? Your Mach number is more than 1 or less than 1?
It's more than 1.
Okay, more than 1. Okay, so it is possible. The flow come up from at the end here. It is possible you get 200. And why? Based on this table.
Yes.
Why?
Because it decreases.
Okay, because the Mach number is more than 1. Velocity in this table, converging passage, is decreasing. So it's possible. Do you understand?
Yes, sir.
Okay, good. Okay, let's move forward. Chong Chong Hongki, you're the next one. Okay. Now, same setting. Your velocity now is 400. Speed of sound 0.1 is 343. Temperature 0.1 is 100 Kelvin. It is possible you hit 200K at 0.2. Chong Hongki, are you there? Okay, answer is possible. Okay, okay. I assume Chong, you understand how it's possible. Okay, I give chance to Joshua. Joshua, are you there? Joshua, are you there? Or Vina, are you there? Okay, let me give them a chance to reply. Joshua, Vina, are you there? Vina, are you there?
Yes, sir.
Okay, Vina, where are you just now? Why are you not answering question just now?
I did not hear, sir.
Okay, okay, Joshua, you stand by. I asked Vina first. Vina, based on the question, okay, based on the screen I show you just now. Okay, tell me. Okay, tell me. I change the parameter. Now, if you're able to answer all these questions, you should no problem for the isentropic flow already. Because there's a table for you to refer. Okay, now if you have this setting, you have a converging passage. Speed of sound at 0.1 is 343. Velocity is 400. 0.1 temperature is 100K. Is this possible when the flow come out from 0.2 or measurement at 0.2, your temperature reaches 300? Is this possible or not, and why?
Possible, sir.
Why?
Because the diameter it's already small.
Okay. Based on this table, how do you know it's possible? Based on this table, how do you know?
Based on this table.
Yeah.
You mean the temperature, sir?
Yeah.
Yeah,
Is this possible to reach 300 or not?
Can, sir.
Why?
Because the diameter is smaller, so it will increase.
No, this table doesn't give you diameter. How do you get diameter?
From
You show me. You show me this table where got diameter.
From the table, the temperature it shows increase.
Okay. So your answer should be by referring to table. Mach number is more than 1, correct?
Yeah.
Then the temperature, because based on this table, the temperature is possible to become increased. The temperature will become increased.
Yeah.
So this should be your answer.
Yes, sir.
Okay.
Yes, sir. Okay, sir.
So again, this table will help you in final exam. So don't tell me you don't know how to answer. Okay, Joshua, you are the last one. So if you're able to answer, then everyone can go home. Everyone can. Yeah. Okay, Joshua. Okay, now I changed the question a bit. Now, you have the same setting, converging passage, same speed of sound at 0.1, velocity at 400. Velocity at 400. So what is your guess answer for V2? Joshua. Joshua, are you there? Oh, Joshua is in the text. Okay. No, Joshua, my question. Can you turn on your mic and not Joshua? Can you turn on your mic? I think you're able to text. Your mic should be okay. Okay. Right, Joshua, you okay? Can. All right, Joshua, we know your difficulty in technical. So okay, I assume Joshua, you know how to refer to this table, Joshua. Okay, good. I think through the series of testing, I know all of you know how to use this table already, which is good. So this table will help you in final exam. So the rest is just using of calculation. Okay. Now the next one is, I want you to go home and read. All right. This one you can go home and read. What happened if you have a Mach number at 1 at the throat here? It is possible or not? Okay. Let me see. Where do we stop? Okay, we stop at tutorial question 30. Okay, we stop at this table. Question which is the tutorial question 30. Okay, we continue next week on this topic again. And all right, so let me stop the recording.